right. Well, it's a pleasure to introduce Jacob Swett. Jake is the CTO of a sequencing and diagnostic startup and is an advisor to Open Philanthropy project on biotechnology, nanotechnology, and biosecurity. And previously, he was a co-founder of Alt Labs, which is a research nonprofit focused on the development and advancement of technologies for biodefense. So thank you, Jacob.
Thanks, Adam. Okay, yeah, so I'm going to talk about biological risk reduction. I'm going to do a little bit of an overview at the outset, but I'm going to mainly focus on metagenomic sequencing, which I thought I'd have to explain a lot of, but I've already heard it mentioned several times today, so maybe we'll dig in a bit more. I'll start by motivating the threat from pathogens if the pandemic wasn't enough, but I am going to talk about a specific type. I'm going to talk a little bit about what we're trying to achieve. I'm going to gloss over the non-technical causes for lack of progress. I'll give you a few of them, and they, of course, relate to our progress on the technology side. Then I'm going to introduce this way of thinking about developing technology in an area such as biological threat reduction, given that you can also create threats using similar technologies. And then talk about how metagenomic sequencing can be a core technology to do this, and give you a little bit of an overview of that, where it's at, what it needs to change to achieve what we want, how some approaches can do that, and some paths forward. So when we talk about biological risk reduction, the threat, mainly what we're talking about are transmissible, high consequence pathogenic agents. These are threats from biology with the potential to kill, over 1% of the population, substantially damage human welfare, or reduce the survival of the human species. And I put some of the definitions down here about what these are. These are generally agreed upon to be some of the requirements, but people could engineer cleverer things beyond this. Transmissible is, of course, just as you'd expect, able to be spread between a human host. High consequence doesn't actually have a great definition, but I'm going to cash it out as this top bullet up here. But we are talking about things beyond a cold. And pathogenic agents, these are agents that are able to cause an infection or harm or alter the host in some manner. I think we typically think about people dying, and that is a very good heuristic for this, but I'll just say pathogens can also do things such as make people sterile, and these would be things I would argue we should be concerned about as well. Maybe you don't actually have any symptoms beyond that, but that would, of course, meet the definition of reducing the survival of our species, which I would argue is bad. And I'm going to also make a case that anthropogenic threats here represent some of the highest risks given optimal virulence theory. There's a theory that basically says things that kill people quickly aren't that great because they don't allow them to transmit as easily. You can obviously have asymptomatic spread, but there's ways to get around this, I think, if you engineer pathogens, and this will set a bar, I think, a bit higher for what we're interested in doing in terms of addressing the threat beyond what you might need to do to, say, address something like the current pandemic. So a little bit about just what is the threat from pathogens. Again, most people, I think, know this, but I wanted to give a little bit of different angle beyond the pandemic, which is that there's several states known to have biological weapons programs. The worst pathogens have ever existed are when people decided to do gain-of-function research, which took the worst natural pathogens and made those even worse. And there's going to likely be increasing capability to deliberately engineer pathogens. Not a lot of people are specifically working on that. We're working on it for a lot of other really spectacular reasons, but this is going to come out of it nonetheless. Risks from accidental and reckless events are increasing. I won't make a comment on the current pandemic. I will, though, say for SARS, the original one, this spilled over more times from a lab than it did from nature. And the last person who died from SARS died from a lab leak. The count right now of known is 2 spillovers from nature, 6 from labs. Those are just the ones that we are aware of. And that's just one pathogen. Of course, the risks from naturally occurring pandemics are also increasing. And that's something I think we should be very concerned about as well. Because historically, pathogens have killed substantial portions of the human population. I won't get into it. Probably everyone's seen this infographic going around online. But a lot of people have died from pathogens. There's some actually estimates that people claim that at least half of all humans ever to exist have died from malaria. That one's pretty hard to substantiate, but I think even if they're off by a lot in order of magnitude, we're still talking about a lot of people dying from pathogens. Now, it is worth saying that the plague is still around. Yersinia pestis, you can still get it, particularly out in the Southwest, but it isn't really a pandemic anymore. And so we have developed technologies to address these, and I would argue that we can continue to do that. We're just going to have to do it in a bit of a cautious way. And I think the way to conceptualize what we're trying to do here, particularly given that there's so many ways for the human body to be disrupted. You heard about some of this in previous talks where it's quite complex, really to have some kind of disease, you just need to disrupt this in some way. And so I think there may be goals that we have in the future which look like preventing people from ever getting an infectious disease. That I think remains to be seen. And I think the way to conceptualize what we're trying to do at the moment is really tilt the offense-defense balance as much as possible, and that ensure that while we're doing that with technology, that we aren't also increasing the risks, or if we're increasing the risk, we're managing that. The goal eventually might be something to end sustained transmission of infectious disease, but this would not only mean that we'd have to be resilient against all pathogens that have existed and will exist, but also the ones that people may create. And so this is like quite hard, but I think if we think about it in this offense-defense balance, we can get into some degree of tolerance in terms of the risk that we find acceptable, or if it's unacceptable, we can try to do something about it. But I do think it's the case that at least as of the knowledge we have right now, there's no single approach that will guarantee success. And so managing this offense-defense balance will be something like what people call a web of prevention, which is a lot of different strategies. But I think we can get this down to a tolerable level. Okay, so I'm going to talk a lot about technologies, really, but I want to talk a little bit about, why aren't we doing things? You could also think of, why did we just have a pandemic? Like, what did we screw up here? There's several causes, none of which is on the own the main reason, but I think these ones start to get at some of them. One is a lot of the innovation that we have for disease really focuses on the individual and not public health. I think the great example of this was what we saw with rapid diagnostics. That also has some regulatory issues, but there wasn't a lot of diagnostics really to help you understand whether you might be spreading an infectious disease. Most diagnostics are meant to help a doctor understand whether they should do something for you. And this is where we have a lot of the incentive systems, particularly in the US. I would argue, and I'm not sure actually everyone in the field would agree with me on this, that there's a big focus on reacting at scale versus preventing at scale. There's a big focus on thinking that we should have the capacity for billions of vaccines to be able to react to the next pandemic. While it's of course prudent to be able to have the ability to do this, I don't think that's where we should be starting out. I think we should be starting out with the ability to prevent things at scale. And I think particularly when you talk about exponential threats, which would be a theme of this talk, having the ability to prevent at scale means widespread capabilities. And you want to have that in place all the time, usually before the threat even exists. And so there's a bit of a challenge here. We were motivated to do Operation Warp Speed once the pandemic was going, but we need to be motivated to have the system to prevent it before the next pandemic happens. So we should be basically doing it now. I would argue also a high degree of acceptance of infectious disease. Probably everyone saw the stats about influenza deaths and people comparing that with SARS-CoV-2. I'm not sure what everyone's reaction was, but I think one of them should be now is that that's a lot of people dying that maybe we should be doing something about. And there's also just a lot of burden of infectious disease in the world. And I think for a lot of reasons that I actually don't have good explanations for, I think we just kind of have an acceptance of this in cultures. We're constantly fighting the last war. This can be evidenced by what we have in strategic national stockpile. It's really just things that we've addressed before. There's a lot of pathogen-specific approaches. I'll talk about a lot of technologies that I think can be pathogen agnostic, which means they can address pathogens regardless whether we've seen them before or not. But most of the kind of development that we've done for specific vaccines or diagnostics even are particular to a single pathogen. And this makes it hard to address the new types of threats, which usually are the ones that are most concerning. I also think there's challenges and there's really no single solution. I'm going to talk a lot about early warning. Of course, early warning is just like the first piece. You are going to have to do something after that. And there's a lot of things that you can do, and I think you can debate about where those are. And those, of course, lead to entrenched interest and people advocating for their own approach. And this, I think, gets to fractured different types of groups and siloed institutions working on this. When it comes to the US government, there's certainly siloed institutions with limited responsibility. I think the pandemic is probably all the more we need to say about what happened there. And then finally, I think there's really pretty generally poor intuitions around the likelihood of these types of events, pathogen dynamics, how they spread, and even immunity. And I think a lot of these things trip us up when thinking about the way we might want to respond to these types of threats. Okay, but when we talk about technology, I want to actually back up a little bit and talk about how should we maybe think about technology in this space. And what I want to argue is that you can generally conceptualize technology, and there's obviously, I think, caveats to this, so I would just take this as like a useful heuristic to approach, is that you can categorize it into 3 different areas, and we can think about how we develop technology based on where they fall within the spectrum. Now, bioweapons are something that I hope I don't have to make the case for, that we need to not develop these types of technologies or be very thoughtful about what we're doing here. And then on the other end of the spectrum, I would say that there's technologies that are what we're going to call defense dominant, which is that they don't typically aid in the development of things like bioweapons or increase other risks substantially. Determining these is actually, I think, quite tricky, but you can make some efforts at it. And for these types of technologies, we should try to figure out how to debottleneck them and accelerate them. But that actually most technologies are going to fall somewhere in the middle. They're going to be what we call dual use, which is that they could be used for good or could be used for harm. And these types of technologies, I would argue that we should do 2 particular things with them. One is we should try to realize them in the safest way possible. And 2, I think we should think about the order in which these technologies enter the world. And I would argue that the order at which technologies enter the world actually is quite important. And a couple of examples I have that are really kind of trivial ones, and you can think of lots of other ones, are thinking about nuclear weapons. There's the kind of famous example that we developed nuclear weapons. We had them for a while, and someone was kind of like, hey, maybe it's not great that these people guarding the nuclear weapons could just detonate it. Why don't we put something on there to make it at least like a little harder for them to do it? And we came up with permissive action links. And I would argue that it would have been much better if we kind of thought through this a little bit in advance. And I think, you know, a smart person could have realized that we needed this. This isn't something that's like hard to spot. I will argue that some technologies might be quite hard to develop the technology in advance, but for many we can. Another great example is cars. I mean, cars were ones where we just developed them, like hopped in them and started, you know, crashing them, killing people, killing ourselves. And it would have been much better if we developed seat belts before. And cars actually, I think, are actually a great example where we've actually gotten much better at the technology now. Now your car has everything from crumple zones to airbags to a collapsible steering column to lane assist and all these types of things. And these are technologies that make the car safer, and that generally we can be thinking about how to do this. Another example that may fall into this is thinking about quantum computing and encryption and thinking about what risk might be coming from that, whether we should do something to our system in advance. The other argument that I'll make is that you can realize technologies along a spectrum. Typically, you have an initial idea, and you're trying to achieve something in terms of a desired function. This could be anything such as a car, and there's a large spectrum in which you can realize this, and that we should be thinking a bit about where technology lands on this spectrum and what we're trying to achieve. Here, I think a really great example of this is mRNA vaccines. mRNA vaccines are a really way to do a vaccine that's fairly safe. This is in contrast to a large group of virologists who are interested in making replication competent recombinant vaccines, which is really just making the chassis to engineer viruses as simple as possible. And I would just argue that, especially with the success of RNA vaccines, that we can have our initial idea of some type of vaccine, our desired function of durable immunity, and that mRNA is just a much better way to realize this, and that we should be focusing on these types of technologies in so much as we can do it. And obviously, there's a lot that you can't control here. You're not policing everyone's research. This is quite hard. New technologies and discoveries will come about. But I think this biases you pretty heavily towards trying to debottleneck the defensive technologies so that you can be as prepared as possible. And I don't really want to stop anyone from making technologies. I think we should just be prepared for it. And the more that we can bias things in the defense direction, the more that we can develop all the wonders from synthetic biology and just realize what we're trying to get from them and not the downside risks, which may be greater in the future. So what are some of the technologies to do this? I wrote this report last year. It's called the Apollo Program for Biodefense. It talks about a bunch of different largely defense-dominant technologies. I won't go through them all. I will say that I think when it comes to technologies for biodefense, it's particularly tractable in that there's a lot of dumb reasons for not making progress in these areas, and that a concerted effort could do something quite substantial in terms of shifting the balance. I think when it comes to natural pandemics, as we're aware of them, we really could conceive of a world without pandemics after another decade. That doesn't mean without infectious diseases. That doesn't mean without outbreaks or epidemics. But I do think we could stop things from going to scale. But it would take about a year, and it would take quite a bit of ambition. People talk about an Apollo program a lot. There's a lot of ways to calculate how much that actually costs. One way to look at it is the percent of total GDP at that time. If you do that, the cost of the Apollo program is somewhere on the order of actually $500 billion at its peak. And so we're actually talking about a lot of money. I'm not talking about anywhere near that much money here to debottleneck these technologies. But I won't discuss all of these. I'm going to try to, in the interest of time, really just talk about one specific technology, which is metagenomic sequencing. And this is because, one, I think it's particularly defense dominant, and that it's a foundational technology. I'll get into this much more with the talk, but sequencing can underlie everything from laboratory safety, if you're talking about being able to detect whether something is leaking out of a laboratory. It can deter and prevent bad actors from doing things. This is work such as what my organization has done, genetic engineering attribution, where we can attribute the lab of origin of engineered pathogens to all these different types of diagnostics. Right now, when you say point-of-person diagnostic, people basically just assume it has to be pathogen specific, and it usually has to be something you spit on. That's really just because that's where the technology is at right now. I think we could have something that eventually is sequencing, and we should strive towards that goal. And then even areas where maybe you think sequencing doesn't play a big role, it does. Everything such as vaccine development, especially with mRNA vaccines, also starts with the sequence. And so for that reason, that's what I'm going to mainly focus the rest of the talk on, is kind of talking about, where is this? Why should we care about it? And talk about some of the bottlenecks. So I'll begin by motivating it a bit, talking about metagenomic sequencing. Then I'll back up and talk about what is sequencing and what are the different types, because I am really particularly interested in metagenomic sequencing. And so we'll talk about why that's important, where are we now, and is it bottlenecked? Well, given the theme of this conference, you can probably assume what I'm going to tell you. And then what are some of the components of this, approaches, and ways to move ahead with this. Okay, so this is a very wordy slide, but it basically lays out, I think, the central argument that I want to make. And it goes like this. So metagenomic sequencing is a powerful technology because all hosts, that's us, and all pathogens have genetic material. And so sequencing can function as a universal detector. And I would say metagenomic sequencing is important, not just because it can be a universal detector, but it can be, it's quite versatile. It can form the core of a layered defense system that we have in our society. And that's not to say all the other things it can do, especially harkening back to the talk before me about, when are people actually getting infected with pathogens? Well, we could figure that out if we had some more capability here. I would also argue that metagenomic sequencing is one of the best ways to shift the offense-defense balance with confidence. And so it's fairly defense dominant, and it can allow us to get much more of the risk reduction in place before we start developing some of the more potentially risky technologies. Metagenomic sequencing has tremendous potential to go through a transformation similar to, say, what we've done with GPS or camera phones, where they're really just ubiquitous, and that there's something really different that happens when we get to the point that everyone carries one of these things in our pocket. The example I'll give is just that when I left the hotel this morning, I didn't want to remember what my room was, so I just took a picture of it. I mean, that's something that you have to think decades ago just sounded like pretty crazy to do, but it's so easy now. And I would argue that we can really realize benefits of metagenomic sequencing if we can get it to this level of ubiquity. And then I'll finally argue that this will probably happen on its own, but we really should not wait for it to happen on its own. And there's a couple of reasons why, and I'll get into those. Okay, I think probably everyone knows what genomic sequencing is, but nucleic acid sequencing is the reading of the genetic material. Sequencing, since it can detect genetic materials of all pathogens, can diagnose infectious disease. Sequencing is one of the few forms of diagnostics. There are some others, I would say not as powerful, such as mass spec, that can be pathogen agnostic and that can detect a pathogen that's never been known before. So SARS-CoV-2 indeed was detected by sequencing. That's when we really kind of knew something was going on. Most things happen after the sequence is obtained. That's when we realize it might be something new. That's when we realize this person who has some kind of ailment actually has an infectious disease and doesn't have something else. And it allows us to also start characterizing and understanding where the pathogen is, and understanding that it is indeed something we should be concerned about, as opposed to a false alarm or a new virus. Metagenomic sequencing is sequencing, but it's sequencing everything. So it's sequencing all the material from a sample. So if I take a sample from you, I take a sample from water, take a sample from anywhere, metagenomic sequencing is I'm not picking up front, I'm going to sequence everything. And metagenomic sequencing is what is essential for detecting novel pathogens, and it's what's essential for biosecurity. But what it's important to emphasize is that all the talk you hear about sequencing is not metagenomic sequencing. Metagenomic sequencing is quite rare. And it's actually for pretty good reason in terms of what we're doing now. If you come in sick into a hospital and I want to take a sample of that and sequence it, well, 99% of that sample is going to be you. And it's going to take a long time and a lot of money to figure out what you're infected with. So at the moment, at least, it isn't typically unreasonable that if you go into a hospital that you won't be sequenced at all, let alone have metagenomic sequencing. Most sequencing is for a specific purpose. Usually you're trying to look for something in particular. Metagenomic sequencing is reading everything. The analogy I give people is this is kind of like, you want to look up something and you know it's in the encyclopedia. And metagenomic sequencing is just like starting from the beginning and just reading everything. It doesn't make sense in a lot of cases that people are typically using sequencing for, so it's not unreasonable. Most sequencing, too, when we talk about it, is human genome sequencing. And there it's important to emphasize that 99.9% of my DNA is the same as your DNA. And so we don't really typically need to read all of it. And most of the times it isn't being read. If you do something like 23andMe, they're not sequencing you. They're looking at specific portions of this that they think are relevant. And just a number related to the pandemic, the majority of the pandemic sequencing has not been metagenomic. It's all targeted amplicon, where we're looking for something very specific, and then we sequence it. And so right now, really only major universities and large medical centers do metagenomic sequencing, and it's really quite rare. Again, just to kind of emphasize like why we care about this, though, and also to give a little bit of foreshadowing to the rest of the talk, which is, here's 3 different types of sequencing that you can do. This is from Illumina. They talk about shotgun metagenomics, amplicon, and target enrichment. And what you'll see here is that when it comes to identifying novel pathogens, really only shotgun metagenomics can do this, and the other ones can't. But they really ding it in terms of speed and turnaround time and scale and cost effectiveness. So this is already starting to give us some hints at what the bottlenecks are to what we want, because otherwise metagenomic sequencing can do everything else that these other types of sequencing can. And this can maybe point us in a direction where metagenomic sequencing can replace some of the sequencing that's happening out there and potentially be commercially viable. But obviously it'll need to be just as simple. So what can metagenomic sequencing do? We've been talking about a little bit in the abstract. I've been telling you that it's important. I would argue that metagenomic sequencing can be a core component of all these different aspects of reducing biological threats. So the first is in terms of deterrence capabilities. Before we even have people thinking about making pathogens, sequencing can be the foundation of what's known as genetic engineering attribution, which is if someone were to release a pathogen, you could attribute this back to the lab of origin. This doesn't obviously give you deterrence by denial, but it does give you some capability for deterrence by punishment. So even at the outset, before anyone's even engineered anything, we can start using sequencing to help with this. Sequencing can also help in another area of high risk, which is prevention of laboratory accidents. Right now, laboratories are pretty well done if you look at a BSL-4, but not incredibly well done. And sequencing could be used much more substantially to understand whether anything is coming out of these labs, particularly given the consequences that could occur if it was a pathogen, anything like SARS-CoV-2 or even worse. I think the main case for sequencing is that it can function as a universal pathogen early warning system. I put up here, genetic material is foundational to life, and that detecting genetic material is key to defending it. And sequencing can really be important here. Now, early warning really just kind of tells you like you have a problem. You still have to do something about that. And typically, once you have an early warning, this is more like a smoke detector going off. And like, no one douses their house in water with a smoke detector going off. You kind of like go try to figure out what's going on. And sequencing, again, here can be quite important. We can imagine a system in the future where we have comprehensive clinical detection for people being sequenced when they enter into hospitals, novel pathogens are identified, and before we do anything too drastic, we start looking for that pathogen sequence in wastewater and understanding whether this sequence is widespread or not, and whether it's spreading, and particularly whether it's spreading exponentially, and whether we should be acting or not. This characterization capability, I think, is actually where we largely failed during this pandemic, in that there wasn't a good understanding of what was going on early on, and there wasn't good motivation to act, and there wasn't good cover for governments and people in the political sector to act without having good data. And so characterization really failed here as well. Now, you'd like to think that by this point, if you deterred it, prevented it, detected it early, characterized it, convinced people it's a problem, and deployed things against it, you could have addressed both problems. But even if you haven't, I would say diagnostics are another area where sequencing can be quite good. Now, right now, hardly any sequencing is done as a diagnostic. You know, the US is doing lots of sequencing for the pandemic right now, but it's never diagnosing anyone. You test positive, and then they send your sample to be sequenced, just so we can kind of understand what we might be in for coming up. Sequencing could form the basis of all different types of diagnostics, providing situational awareness. Then, as I mentioned earlier, sequencing is also foundational to medical countermeasure development. Moderna got a lot of press for developing their vaccine, which is in a couple of days of getting the sequence, and that's impressive. And now we're having goals of 100 days to a vaccine, which is just great. But I think we should also realize that it was at least 41 days from the first known case of SARS-CoV-2 before we even released that sequence. And so even if we're targeting 100 days for that for vaccines, I would argue that we should be doing much more to detect early. December 1st is just the first known case. Cases were probably happening in November. And so you could imagine a world that looks very different going ahead, where we would have detected something like SARS-CoV-2 in November. We had our vaccine sometime in February, and it was a news story that really none of us here even heard about or discussed. And that's what I would argue is what we would like it to be in the future. And so essentially, sequencing has a lot of capability to help prevent pandemics, whether natural, deliberate, or accidental. I won't make the case that it can do it all on its own, but I will argue that it's pretty fundamental to it. And I think it can do this through comprehensive layered defense. I think we want to have sequencing moving out of the clinic into all these different areas, and that we should be doing sequencing pretty much everywhere. We should be doing it environmentally. We should be looking at wastewater, waterways. We should be looking at agricultural threats. We should be looking at places where there are transit points, high density events. This HVAC is probably sucking air back in and pulling some of the condensation out. We should be looking at that so we can know that anyone here is infected or not with anything. Definitely in the clinical setting, we should be doing much more sequencing. The world that we envision is the one where you kind of go in and sequencing is so useful, which it really isn't yet, that we find it just as useful to take your sequence, sequence you metagenomically, in addition to taking your weight, temperature, and other core biological functions. Some pathogens that certainly exist already and some that could be engineered may have very, very long asymptomatic periods. So we don't want to rely just on clinical sequencing for people to show up. And so you also want to be looking at people who are in high transmission and high risk populations for asymptomatic infections and be doing a survey of this to understand what's going on. You should be looking at vectors. These are very good ways to spread infectious diseases, mosquitoes, fleas, all these different ones. Sequencing should be part of diagnostics that we're doing for other things so that we can, whenever you're testing just to see how you're doing, looking at your transcriptomics to see what's going on in your body that day. If we were doing that with sequencing, we could also be using it as a point-of-person diagnostic by anyone anywhere. And in laboratories, this is an area where some of the risk is the highest, and we should just be sequencing anything going into and out of these laboratories. And I think the way that we should think about what this should look like is what we do for other threats that are on comparable scale, which is nuclear weapons. So if you look at missile defense, we have very comprehensive layered defense in terms of detecting things. And in fact, when people started looking at the threat of nuclear weapons, they didn't kind of wait and see, what are we is some kind of technology going to come along that's going to allow us to address this? What are we going to do? It's like, no, we developed space-based infrared sensing so that we could detect thermal signatures anywhere on the planet within seconds of launch, and then are able to track them anywhere in the world and then address them. And this is something that the United States government has space-based infrared sensing alone, which is not all of missile defense, which is projected to cost around $170 billion this decade. Space-based infrared sensing has cost us around $20 billion. I would argue that if we think that money is merited for that type of threat, we should be doing something pretty similar for biological threats. And just kind of one example of what one component of layered defense might look like is this concept of ThreatNet by Dave Ecker. This is a metagenomic-based system based at 200 urban hospitals. If you pick these hospitals strategically and you sequence everyone that has an ICD-10 code of pneumonia of unknown origin, then for about $1 billion a year in the US, you have a 95% chance of detecting an agent if only 7 people in the country seek care. And this is something that will only be cheaper in the future. And this I would argue, is something we should be doing already. And it's just one aspect of the layered defense. So hopefully you think this is like great, but it's like, so why don't we just do it? One thing you might be asking is like, where are we now with sequencing? And I think the way to think about sequencing is maybe through a couple of analogies with GPS and cameras. And so, like, yes, we have sequencers. Everyone knows that. But I would argue that right now where sequencing is maybe where 1990s was for camera development. And I would argue that that's a very far cry from where we are now with cameras in our pockets. And so, like, sure, if you're a professional photographer, you can have a really nice camera. Companies have these types of cameras, but the average person doesn't. There's just so many things that you get once you push the technology to this. GPS is another thing. Maybe we want the kind of Google Maps equivalent to understanding the pathogen world around us. And that took a big change in GPS technology. I mean, GPS technology existed for a long time, but we hadn't gotten to the point yet where, like, my grandpa can pull out his phone and press a button. And sequencing is nowhere near that. Sequencing is really more like this guy over here, carrying around a big portable backpack. He's been trained specifically to do it. And, like, sure, you can pinpoint your location, but that's a far cry from being able to do it easily. And I think to get to the layered defense that we need, we'll have to have this ubiquity and accessibility with sequencing. You might be surprised at what I'm going to tell you coming up next, that like sequencing is nowhere near where it needs to be to do this. It's probably because you read articles like this New York Times where George Church has told you that sequencing is 10 million times cheaper, and that here they're already saying that in the midst of chaos and a global catastrophe, the age of cheap rapid sequencing has arrived. Well, let's look a little bit about some of the numbers. So the fact that sequencing has dropped 6 orders of magnitude for a human genome is absolutely true. But if you were to go to a hospital right now and do metagenomic sequencing for a respiratory pathogen, it would probably cost somewhere around $500 to $2,000. Other numbers are to run a sequencer for one operation a week for a year would cost you anywhere around $100,000 in reagents. Genome sequencing for rare diseases or cancer costs around $7,000. There is a sequencer that you can buy for around $1,000, but there's a little bit of a catch in that I worked recently with a project to set up accessible genomics, and when we crowdsourced this and talked to almost everyone, the cheapest you could get a lab to set this up was another $22,000. And so there's quite a bit more to be done here. A couple other numbers that I think to help put it in context, any sequencing right now really requires extensive training and typically several specialized individuals. Sequencing runtimes often take 12 to 72 hours. It can take anywhere from like 6 to 12 hours just to do a single analysis on one of the smallest sequencers there is. This is one that it might be hard to believe, but there's really only one single vertebrate that had its entire genome sequenced, and that's humans. And that paper is under review at the moment. And so we had the Human Genome Project. There is still about 8 to 10% left we're still trying to get, and there's still actually a little bit left still. And so while we're doing a lot with this, there's still a lot left. And only a handful of labs are really even kind of developing the algorithms needed to do metagenomic sequencing, and so it's quite slow. I mean, here's an example of a typical advertised, like, this is good, you should pay us for it, workflow. And I won't go through it all. I'll just point out that it starts with day 1 and ends with day 3. And so this isn't anything to detect anything quickly. I mean, this is the equivalent of like taking the picture, taking it to the photo center, having it developed and come back. You're never going to take a picture of your room key if that's how this works. You need to have something different. Just one other slide on what the numbers are. Sequencing right now, it's hard to get the exact numbers because not all companies are public, so you can't get all the data. But there's probably around 30,000 NGS systems in the world. This is like PCs circa 1970s. This is not a lot of systems. Only thousands of units are placed annually. There's 7 companies that produce NGS systems. The majority of these companies actually only place a few hundred units a year. If you look at this paper, they actually tried to document all the sequencers, and the entire continent of Africa only has around 200. And if you look at sequencing for SARS-CoV-2, at least 40% of the sequencing in the US is being done just by 3 institutions. So, like, yes, there's a lot of sequencing going on, but this, again, is not quite where we want it to be. The majority of sequencing, with the pandemic being a little bit of a rare exception where we bought all the sequencing capacity off scientific labs, is done for scientific research. That's more than 50% of all sequencing. It's not quite where we want it to be, but hopefully I've convinced you that it could do really nice things for the world if we got to where. So how do we do that? Well, so when you go and talk to people about what are the bottlenecks to sequencing, they'll tell you all these types of things. I won't go through all these, but they'll tell you things like, well, it's virus degradation. But I think the problem there is that people take the sample to the sequencer and we don't take the sequencer to the sample. This is telling us something about. People will tell you that cold chain is an issue. Well, cold chain is an issue because we've decided that we needed to do sequencing with reagents. We can conceptualize ways of doing sequencing without it. We're also thinking that infection prevention is an issue. If this person is really sick with something we're concerned about, we don't know it, we need to have infection prevention built into the sequencer. But this is just because someone else has to sequence you. You can't sequence yourself. And so I think these are getting to more fundamental bottlenecks. What I would argue is that most of the bottlenecks actually come down to these components. I think typically what you get when you ask people about biotechs is you get the kind of apocryphal Henry Ford quote, which is that if you ask people what they wanted, they'd say faster horses. People want just reagents without cold chain instead of just getting rid of reagents. I won't go into all the nitty-gritty details, especially given the time, about sequencing, but I'll argue that these are the specific aspects to focus on. And you'll notice here that cost isn't here, because there isn't really a specific cost aspect to be focusing on. It really comes down to focusing on the consumables and the complexity. Much of the complexity for metagenomic sequencing is because you need someone with a PhD, sometimes a PhD and an MD, to be running the sequencer, and that our problems are really in terms of things such as sample preparation. And so how do we approach these different aspects of the bottlenecks? Well, I would argue that we should look at the fundamental components of sequencing and break these down and figure out where we can push ahead and make progress on each of them. Right now, I've broken into 4 basic components, but I think it's important to emphasize that interdependencies exist between them. And so oftentimes we focus just on one. Oftentimes we just focus on the sequencer, but better sample prep can lead to easier analysis, and certain forms of sequencing could even lead to us not even needing to do certain types of sample prep. And so we can look at these different areas and figure out where we can actually make progress with sequencing. And once we make progress with sequencing in general, we're also going to need to make progress with the integration of the outputs from these sequencers to understand what's going on, say, across the country. I'm going to mainly focus on just 3 of these aspects: the sample acquisition, preparation, and analysis. And that's largely because there's a lot of advances going on in sequencing due to other incentives and applications that I think can be leveraged by biosecurity, although plausibly suboptimal. And the story I have to tell about sample acquisition, preparation, and analysis for metagenomic sequencing for biosecurity is that they've been very neglected, and so this is actually an opportunity to do something with them. So for the approaches, I won't go through everything on the slide. I'm just going to go through some of the colored ones here to make the point that I think there's a lot that can be done here, and these approaches could be areas where we could put more effort. With sample acquisition, basically the story is like there's no innovation going on here. You typically just get a sample from a patient, and that's where most sequencing is done. If we can innovate for all these different areas, we can ensure that sequencing ends up being deployed in this layered defense mechanism, and that we should really be thinking about things like in situ sequencing, and that we really just need to remove the need for any human to be involved in sequencing, unless it's like diagnostics, in which case they would be using it on themselves. Sample preparation is an area where it's very complex. I talked about that really cheap $1,000 sequencer. It's actually about the size of this. It's called a MinION, portable and everything. But what they don't tell you is that this is how many reagents and other things you need to bring along with it. So sample preparation is a major bottleneck to sequencing in terms of moving things along and in terms of cost. And here, I think, again, there's tons of things we can do. We can break this down into the core components of what we're trying to achieve. But I would argue that some of the most important things that we should do is, one, we should just automate it. There shouldn't be people taking tubes between different samples and introducing contamination, and that we should really move away from reagents to knock the cost down, but also to make it so that sequencing can be deployed and doesn't have to be replenished. This is an area where I actually did my PhD on in terms of electrokinetic methods. There's all sorts of ways actually to manipulate, to do pre-filtration, lysis, isolation, separation, and concentration, all with phenomena that don't require reagents, but there's really not a lot going on in this space at the moment. Sequencing, there's a lot going on here in terms of innovation, but again, if we want to try to get to this metagenomic sequencing and realize all the benefits here, we're going to need to get the throughput up by probably about 1,000x again. Thinking about things such as selective sequencing, where we start to sequence things, figure out what we have, and then stop sequencing things, and not just do a big monolithic run. And in terms of analysis, again, I think there's a lot that we need to be doing, particularly if we anticipate the advances that are going to be coming. But I think one of the most important things that we can do, because I think analysis is one of the areas where we can leverage most other technologies, is we should be developing what I call SPUs, sequencing processing units. These would be like the equivalent to TPUs for machine learning. We should be developing specialized hardware to be not only handling the data that comes out of this, but also to handle the information coming off the sequencer in real time and being able to react to that. So this hopefully sounds great. The question is, why isn't this happening? Well, again, I think this is just a list I showed you at the outset. I think there's all the issues with biosecurity in general. I also think that when it comes to sequencing in particular, there are these bottlenecks. I think there's poor coordination. There's actually a lot of stuff going on in this area for microfluidics and different ways of doing sample acquisition, but none of it's really for sequencing or isn't really being applied to it. And so I think there's a coordination problem here. One of the main motivations for sequencing is, I think, metagenomic sequencing is really realized as public good for rare high consequence events. And so I would argue that there isn't much of a market for it at the moment. Many of the commercial aspects of sequencing that you could have right now really can be achieved by other cheaper methods that are more available. So technologies such as PCR, and so that's why they're being used. You could use sequencing for it, but due to aversion to new technologies and the fact that this already works pretty well, except for in the rare events, you'd have to get sequencing to be cheaper than a multiplex PCR panel and get clinicians to trust it, and that's just a very high bar for any company to going towards. Also, I that there was poor integration and translation of the fundamental science. I actually think when it comes to sequencing, NIH is doing a really good job at the fundamental level, but we don't have any translation towards the public good aspects of this. I think there's no sense of urgency around. Many believe that it will eventually happen, and I think this is true. But if I harken back to the missile defense analogy, I don't think we should have waited for satellites to become a thing and IR detectors to be there. We innovated them and brought them about. I think it is fair to say that sequencing is still pretty early on, and that just a couple of years ago, contemplating these types of layer defense would have come up with numbers that are fractions of countries' GDP, and so possibly it's quite new, and so this will get more momentum soon. I do think when it comes to the value of metagenomic sequencing for early detection, that this is pretty poorly appreciated when it comes to exponential threats, and so we don't see as much motivation to be detecting things early as we do to be able to react to them. I think really when it comes to at least biological threats in the US, that no one's really specifically responsible for addressing these issues. That again, I think was something we saw with the pandemic. There's also a number of institutional bottlenecks. I'm happy to discuss these more. These actually get to pretty specific people. If you talk about NIH, DARPA, BARDA, CDC, there aren't a lot of people who fund sequencing in this space. It's maybe 10 people, 5 people at certain ones, and there's a lot of reasons why this isn't happening. It's hard to have a company in this space. There's a lot of consolidation of the intellectual property. There's aggressive litigation. There's poor markets for pandemic prevention and diagnostics. Academia, they're pretty pathogen specific and they focus where the funding is. And advocacy, and when it comes to pandemic prevention, really is not really focused on technology. We get a lot of pushback when we talk to people about this. They don't think they're technological problems. I won't go too much into the path forward, but just to say that I think that without intervention, sequencing technology for biosecurity is really unlikely to end up where it's needed, by when it's needed, and in the form we need it. I think if we let other types of demands drive sequencing to the coverage that we eventually want, we're going to end up with suboptimal technologies locked in that will make it even harder to have the kind of system that we want. I do think an FRO would be a good option for this. I also think that DARPA programs could be quite successful. We're actually optimistic about maybe a potential new program manager in this space working on this. Other ideas could be pre-competitive consortia. Should we have a Sematech for sequencing to be moving this along? I think we should probably be doing pilot programs to start realizing some of this benefit and identifying some of the additional bottlenecks and getting a better grasp on the situation. I'll just end by saying that I think if we fail for all the things that I mentioned for biosecurity and we just happen to advance sequencing, we still did pretty well, shoot for the moon, land amongst the stars, we would make progress in all these different areas, which I think could be quite good. And so I think there's a really compelling case here to be working on this. I'll just end by thanking all these people who helped me come up with this presentation, discussions, and the organizers for the chance to speak today. So, thank you. Oh, and if you want to read more about the non-technical sides, there's a bunch of resources in the presentation, and I'll make it available for people.
So Ian is a chemical engineer. He has started two successful battery companies. He worked at Gates Ventures for a while, and now is leading an applied science group called Orca. And he'll be telling you about food without agriculture.
Good job. My topic is climate adaptation. So I'm going to start with a few super pessimistic slides about how we should prepare for a warming world. But then I'd like to focus in on one particular climate adaptation technology that I think we should have, but we don't already. And that's synthetic methods to create edible molecules without agriculture. So to begin, 3 reasons it's worth thinking about adapting to a warming climate. First, reducing carbon emissions might happen more slowly than we're all hoping. Baseload, geothermal, or nuclear could really help decarbonize the electrical grid, but that's just the start. There have been a lot of very ambitious projections, but the actual renewable share of total U.S. energy has only gone from 5% to 10% in the last 40 years, and it's not totally clear that it's about to hockey stick upwards. A second concern is that there's kind of a tragedy of the commons dynamic with respect to climate change. The rich countries of the world have not been super fast to pay the premium to decarbonize their own economies, and they might be even slower to pay to subsidize energy transitions in the developing world, which is actually where we expect the majority of carbon emissions to come from in the 21st century. So it's not impossible that countries keep on paying lip service to long-term global interests, but actually prioritize their own short-term national interests. And that tragedy of the commons is kind of made explicit in some of the economic models in the time domain. The physical time constants of climate change are very long. So when we make investments in mitigating climate change, those may not pay for themselves in terms of offset climate damage for about 60 years. And that time scale doesn't have anything to do with the cost of the innovation that you're applying or whatever you're rolling out or the climate damage. It's just all about the heat capacity of the Earth. So we should keep in mind that for decision makers like trying to be helpful with decarbonization, none of that will really pay off anytime in their professional lifetime. And lastly, even if hopefully we fully decarbonize the energy system really quickly and then start doing giant net negative emissions investments, there's still aerosols and water vapor additionally in the air that as they come out, they'll lock in about twice the climate change that we've experienced already. So at very least, I think it's worth adapting to that. Climate change gets a whole lot of airtime, I think, and I feel like bottleneck analyses you could do in all kinds of topics. But I think I really want to focus on the last one today of securing the global food supply. As the world gets hotter and drier, if farms don't relocate, yields will decrease. And that's without even thinking about kind of the catastrophic things that could happen like dust bowls or droughts or farms turning into deserts. So I wanted to focus on this area. I think it's a little underserved actually because it's one area where climate change of just a couple degrees really could impact the habitability of the planet. To start, I think this is the conception most people have of how food is created. Agriculture is like a planet-sized solar panel for turning sunlight, CO2, and water into edible molecules. It takes a huge amount of land and water and is fairly polluting, but this is the picture most people have at least. But I think in the modern world, we have to amend that picture somewhat because the amazing agricultural yields we're getting in the developed world now are in part due to really big subsidies in energy that we spend on agriculture. That's like fertilizer we're using for farms, mechanical work input, irrigation. A famous number for the United States is that for every calorie of corn we produce, we're spending 5 calories worth of fossil fuels on the cultivation. And that's an especially bad one. But on average, crops across the developed world consume more energy in fossil fuels than we get back from them in terms of food. So I just think it's worth asking the question if agriculture might be unstable with respect to changes in climate, not a reliable food source for the future, if it's already takes a lot of land and it's quite polluting, and if we're putting more energy into it in the form of oil than we get back in the form of edible calories, is it worth thinking about whether or not there might be some way to produce edible molecules directly, maybe from oil, maybe from CO2 and sunlight, but without the plants entirely? I feel like things like Impossible Foods or the lab-grown meats, or even people growing algae in vats, I don't really feel like that counts as synthetic foods without agriculture. Like Impossible Meats or lab-grown meat is kind of upgrading one agriculturally produced food stream into another one that's of higher value and higher nutritional value. but the world actually doesn't really have any significant ability to create food without plants. And so I want to jump into this anecdote from history, which is that in the 1940s, when World War II started getting really rough in Germany, a chemical plant in Western Germany started taking a waxy byproduct from this Fischer-Tropsch process that they were using to turn coal into diesel fuel, and they oxidized that byproduct in air to make a fatty acid, and then they esterified it. They added it on to synthetic glycerol to make a triglyceride, which is the most common form of edible fat. So after like cleaning it up and testing it on people and seeing that it wasn't generally safe, they rolled that out and produced it on about like a 2-ton per day scale for the remainder of the war to feed their people. And I think that was really the first example in history of people kind of getting an independence from plants as a food source. And it really made sense for them at the time because as catastrophe food, fats can feed a person up to 80% of the calorie intake that they require. It also was an economical process for them because the feedstock was basically free. But that plant was destroyed at the end of World War II, and that idea of feeding fossil-based products kind of resurfaced occasionally in the Eastern Bloc in the subsequent decades, but it's really gone from the earth now. There's really only one instance in which we eat like large quantities of a synthetically derived food, and that's methionine, which is an amino acid, one of the building blocks of proteins, and it's produced in bulk mostly as an additive for livestock food. But otherwise, that synthetic foods process has kind of vanished from the face of the earth. But attention is kind of returning to it now with some startup activity, and it's mainly in 2 categories. The first one I will call fossil foods. It's companies like Callista that bubble methane into big vats of methane-eating bacteria. They add ammonia to, and then they'll scoop off the microbes and feed them to fish as a kind of a source of base calories. There are also similar efforts doing things more renewably with bubbling hydrogen and carbon monoxide that could be produced renewably into vats of different microbes, but that metabolize those things to make food sources for humans. Those companies have to target humans because while renewable electricity can now be cost competitive with fossil electricity in certain times and places, renewable chemical energy is still much more expensive than fossil chemical energy. So those efforts will have a harder lift. Really, I think both of those projects are extremely cool and just kind of paradigm breaking and reducing our reliance on agriculture as a source of calories. But to be honest, I'm not sure if either of them could really work out. One problem is that methane and hydrogen are both vanishingly soluble in water. So to grow microbes in that, to get any kind of throughput with a biological process like that, you need a giant capital expenditure on a big plant. Okay, well, if I was to map out the general landscape of how you might produce synthetic molecules without agriculture, I'd say there are kind of 3 big choices you'd make. The first would be the choice between chemical methods and biological methods. Chemical techniques, like in the petrochemical industry, you can get to regimes of temperature or pressure or rate constant that are very, very high. So you can make simple products with really, really high throughput. Biological techniques, more like things we see in the pharma industry or maybe breweries, much better at creating like very specific compounds, but tending to have a lower throughput. There's also a choice of fossil feedstock versus renewable feedstock. You see there are startups now doing both, but in general, there's a thought that renewable feedstock might be the future, but if you're actually just respiring fossil carbon, it's actually a surprisingly low carbon impact, and it might work for certain beachhead markets. A last kind of basic foundational choice in like what synthetic foods you'd make would have to do with whether you're producing fats or proteins. Fats have a generally lower sale price, but they're simpler molecules and much more amenable to chemical processing, and they're easier to purify. Proteins, there are 20 of them. 19 of them have left and right-handed forms, so some purification is required. Methionine is chemically produced at scale now, but otherwise those techniques are kind of a heavier lift, or those products are a heavier lift for chemical techniques. And here's a census really of efforts that are out there now in producing synthetic foods, kind of omitting synthetic methionine, which has been around forever and is a global industry. Of those 11 startups that I know about, I hope there are others in stealth mode doing kind of cooler stuff, but they're really all biology startups, biological techniques focusing on production of proteins, and kind of maybe riding on the coattails of a lot of the proportional enthusiasm about cell-based meats and cell-based fats that are being produced. But it's really conspicuous that there's no analog to that 1940s German project that was so successful around now. So I just wanted to analyze what a chemical synthetic fats process would look like if you did it today. And I think unlike the German project in the 1940s, you wouldn't piggyback off that Fischer-Tropsch synthetic fuel process. You certainly could, and as more of those kind of sustainable aviation fuel type plants come online, you might consider it. But I think what you do is use the Ziegler process, which is how we make polyethylene or most detergents. We're able to make fatty alcohols, which are one oxygen atom away from fatty acids, at a price of about 50 cents per kilogram using Ziegler polymerization when we make detergents. And it's not new technology, but it's not especially well known. Oxidizing those fatty alcohols one further step to make the fatty acids that could be esterified to triglycerides would be a pretty basic chemical process to add on. And unlike the process that the Germans pioneered in the 40s, you'd have a lot of flexibility to, if you were trying to make a process to make a extremely cheap source of base calories for agricultures or for cell growing media, you could use the ultra cheap natural gas feedstock. But if you wanted to maybe make a cooking oil and need a gloss of virtue signaling on your product, then you could conceivably hit the prices you needed to for some higher price beachhead markets with feedstocks like municipal solid waste or air captured CO2. So I had a process engineer look into turning the contemporary detergent making processes into a process for making sustainable fats. And it looks like the price you could get is really dependent on the feedstock you use. But using natural gas at prices now, it looks like you could beat palm oil, which is the cheapest source of edible fat now. In terms of using renewable feedstocks, there would be kind of a green premium to doing so. The cost there for the CO2 derived product equates to a carbon price of about $30 per ton of CO2. So it could be worth doing. So there's a group called GI Research Triangle Institute that builds chemical pilot plants. And so they've built petro soap, detergent plants before. So this is like a very conservative estimate of what that cost for that one extra oxidation step is to make the fatty acid from the fatty alcohol used in making detergents. And then esterification to triglycerides. There's a food additive called Olestra that scaled up that process in the 90s and 2000s. That is the price for the refined product. So the unrefined product could be like 20 cents less. I put 2 dates on there because those move around a lot. I feel like there's a lot of pushback, and in particular, there's a search for sustainable sources of foods like palm oil, which are commonly perceived to be obtained at the cost of deforestation in places like Indonesia. So I think there's an environmental benefit to doing so. Synthetic foods in general are something that really almost no one thinks about, and I would like people, I'm not pitching this fats project in particular, but it is one particular aspect of synthetic foods that seems strangely unlooked at.
No one eats insects, right? And why is anyone going to eat synthetic food?
I think there would be a really big optics problem. I think if you could, there's air captured CO2 used in vodka now, and people perceive it as virtuous to kind of support this unusual method of obtaining the carbon in their vodka by buying this product. And I don't think it's inconceivable that you could say that, an air captured palm cooking oil or an omega-3 fatty acid supplement or some other source of bulk fat. I guess to jump ahead, I'll just jump ahead. I see 3 real reasons for this type of food. If you have an environmental perspective, then one kind of sounding number is expansion of agriculture necessary to feed the world in 2050, even without climate change, will cause more biodiversity loss than 3 degrees of climate change. So being able to make food without cultivating, 50% of the habitable land of planet Earth is a lot to invest in a process that isn't that remunerative. And if we could create food without using all that land, I think that would be great. For business people, there might be a case for making cooking oil or some kind of higher priced fat, and certainly there is for certain proteins. And for the catastrophe-minded, or if you wanted to travel in space, I think it'd just be a good like capability for humanity to have, to be able to live places that plants couldn't thrive.
I think the point Tyler raises is a very good one. We don't want to eat inorganic stuff, I think. I think it's our bias. I think we kind of judge the status of people a little bit by what they eat. This is one of the biggest problems also of like the insect-based diet, right? Mm-hmm. It feels undignified. It doesn't feel like it has life energy and all of that. If I were trying to say frame this, I would try to figure out how to make astronaut ice cream out of this. And you'd be like, you know, astronaut ice cream made basically out of moon rock or something like this, some product that is associated with space exploration. I think sort of more people might want to eat that, or it might just be disguised in normal industrial food. And I'm curious whether there's any interest in, say, NASA or other places in that.
Oh, I mean, I've never looked. I think that's a good point, that as space food, this would, you just like jump over all those hurdles having to do with optics, because it'd be kind of the only option to use recycled CO2 to make food. I definitely think, I mean, that company Callista now is making fish food based on natural gas, which I think is, if they can make it work at scale, is a great idea and is actually good for the environment and may be profitable to them. So animal food would be another market.
Oops. How much do you think about sort of the nutritional value? Like, I think I use Soylent as an example of like, well, you know, all we need is protein and fat and, you know, these minerals. And then knowing sort of biology and our knowledge of nutrition, nobody in the world knows what the human body needs. And so when you make the reductionist version of it, you are guaranteed to be wrong. Maybe only a little wrong, maybe a lot wrong. This is probably going to be a lot closer to what we would have eaten anyway, but like, how sure are we that it's close enough?
Yeah, I guess I framed this poorly. I'm not suggesting that you all start eating this sludge that the Germans were producing in World War II. I'm saying that, you know, there are a lot of companies making more elaborate products that might be healthy and could be really good. Palm oil right now is a chemical, palmitic acid, mixed with oleic acid. We can make those exact chemicals and avoid, you know, 2 or 3 gigatons of CO2 emissions per year, save a lot of rainforests, and maybe make money. I think it would be looking not at the level of like selling a food to a consumer, but at Unilever, like you mentioned, like looking at this like a chemical feedstock, and just as an important capability to have for if things got worse. When we eat food, we're respiring about 1/3 of a gram of CO2 per calorie we eat. And so if you have a chemical process making food from something like natural gas with any kind of like normal chemical carbon utilization, your effective CO2 impact, even if you're respiring fossil carbon, is quite small compared to, you know, eating palm oil, that carbon is in theory at least, you know, grabbed from the air by a plant, built into an oil and then fed to you. But in practice, you know, the numbers for carbon impact of plant-based foods are 1 to 5 kilograms of CO2 per calorie grams of CO2 per calorie you get. Making this kind of chemical feedstock either from captured CO2 or from even from a cheap feedstock like natural gas, I think, well, obviously good water and land-wise, but could be really helpful greenhouse gas-wise. That's it for my presentation, though.
In a scenario where you converted CO2 to food and you used renewable electricity for that, you get a benefit of capturing that CO2, so it's kind of carbon negative food, and you free up the arable land for other sequestering. Like, what's kind of the net benefit there?
I think it would just be in land use, and then if there were externalities to agriculture, like fertilizer and tilling, you know, the fact that we spend more than a calorie worth of oil in every calorie of food we cultivate to begin with makes it a win as long as it's about 1-to-1. But I wouldn't call any food carbon negative. I think the best you could do is carbon neutral, because we eat the carbon and then we respire it back out. About 6% of all anthropogenic greenhouse gas emissions is us breathing.
Right.
I feel like there might be like a couple things that are getting conflated here, right? One being a hedge against the good arable land moving around, right? Such that like we need to produce food independently of where the good land is, because that's going to move around in unpredictable ways. And then separately, is there a better way to produce food that is currently either be very expensive, very deforestation intensive, very carbon intensive, and they're sort of separate, because if the argument is we're going to make this food because we want to reuse this arable land for other stuff, like it's not helpful if the land doesn't stay arable, you can't actually plant trees on it or so on. Like, I guess I'm curious if you think this makes sense to pursue like now, literally for palm oil, or if this is like a hedge we should have if arable land moves around enough that like we can't trust it to exist.
Oh, so with the arable land, you're saying that like you couldn't rely on being able to reforest agricultural land that was displaced for climate reasons. That's probably right. I think those reasons, I think they all kind of make sense. I think it's something we should know. We shouldn't be slaves to plants for our food in all circumstances. It's probably good for the environment to do this now, and there might be a good business in it.
What about carbohydrates?
Sale prices of fats are around 90 cents per kilogram minimum. Sale prices of protein are like 90 to $1.80 minimum. Sale prices for like the simplest carbohydrates like sugars is like 30 cents per kilogram. In addition, glucose, so the simplest one you could think of, you have 4 chiral centers, 4 places it could be a left-handed or right-handed molecule. So even if you get all the atoms in the right places, for every one way of putting it together right, there are 15 ways of putting it together wrong. It's 2 to the 4th. So it's just a much harder project. I know that you can eat the wrong chirality of protein and get calories from it, but you can't build it into your body. And the transamination pathways in your body, in some cases, can take like the wrong chirality of methionine and convert it into a different amino acid that it will get used from.